Hey folks, welcome to the Neo4j Twitch channel. My name's Will, and today we're going to pick up where we left off last time, building a real estate search app with GRANDstack. Um, let's just jump right in. So GitHub, Johnny Montana, Willow GRANDstack. Let's paste that in the chat. Okay, so there's the code. What we did last time, so just if this is the first time you're tuning in, to give you an idea of what we're working on a GRANDstack application, so that's GraphQL, React, Apollo, and Neo4j database. Oops. The architecture looks something like this, where the front end of our application is a React application using Apollo client to query a GraphQL API that is using this library called Neo4j GraphQL.js, which makes it really easy to build GraphQL APIs on top of the Neo4j Graph database. Inside Neo4j, we have some data on parcels, so like properties that are for sale and users searching for them, that sort of thing. So you can think of this as kind of like a clone of Zillow if you're in the US and you've seen real estate search apps like that. But there's a few different ones where we're basically searching for properties that are for sale, viewing some details about them. Cool. So we've been on this journey. Let me jump into the data directory on GitHub. So we've been on this journey of importing kind of like a base layer for our application that consists of property parcels, a lot of geospatial data, so the boundaries of the properties, the latitude, longitude, single points of where they are, information about the size of the lot, what city it's in, that sort of thing. So we pulled that data down from the state website. Initially, we were just doing one county just to sort of figure out how this works. So we pulled that down as shapefiles, converted that to GeoJSON, and we started importing that into Neo4j using the APOC load JSON procedure, which lets us stream in JSON data and load that into Neo4j. So this was nice. This was, I thought, a really nice way of going from binary shapefiles to a more human readable format and importing as JSON. Okay, cool. So then we did some things like figured out what city the properties are in. We pulled in the latitude and longitude, really a list of latitude and longitude as a polygon property. And then we also set a location property with just a single point. So to kind of cheat, we just grabbed the first property in our list of points for the polygon. And then we were doing some queries in Neo4j. So for example, let's say given a point, this is GraphQL Architect. We'll come back to that later. What I want is Neo4j browser. There we go. So this is Neo4j browser. So here's our data. Let's do a call DB schema visualization. Right. And what happened there? Oh, right. The same thing that happened last time where I added some additional indexes. That's okay. That's fine. We can just ignore. Well, we'll talk about in a minute where these business category review and user indexes come from, because this is a good example. If you remember last time when I opened up our database, we had a bunch of extra data and extra constraints in there. So we'll talk about where that comes from, but ignore that for now. For now, we have style reset. We have just this data. So property nodes that are in a city. Let's just pick some properties kind of at random here. So here's one that is owned by LB Cattle Company. So this is just vacant land. There's no address attached to it, so we don't know what city it's in. Let's pick a city. Here's Big Sky. If we traverse out from Big Sky, we can see, okay, here's a bunch of properties in Big Sky. If we pick one, we can see some more detailed information, and including the boundaries of the property. Okay, cool. So that's kind of where we were last time. We can run some geospatial queries in Cypher. So here's, let's say, given a point with latitude and longitude, this is how we construct a point in Cypher. And we can look at this on a map just so it's clear where we're talking about here. Latitude, comma, longitude. Okay, so here's this point. This happens to be Montana State University, just where this point is, in the city of Bozeman. Let's zoom out real far so we can see exactly where we're talking about here. So this is in Montana in the US, and the county that we pulled in data is Gallatin County, which is, I don't know, like roughly this area on the map that we have data for. So anyway, so given this point, which happens to be in Montana State University, let's find properties that are within a kilometer. Well, that looks like this. So match on a property where we have location and the distance from this location point and this point from Montana State University is less than 1,000. So distance by default is measured in meters. So this is where the distance is less than 1 kilometer. Cool, here's some properties that are less than a kilometer from the university. But we can also work with polygon geometries. And so towards the end of the session last time, we installed this spatial algorithms library. And this adds some procedures into Neo4j that allows us for doing things like point in polygon, working with distance between polygons, polygon intersections. I'll paste this in the chat as well. Cool, so we installed that last time and we saw an example query like this that now says, okay, so for a given point, we want to know what property that point belongs to. So we say match, make this a little bigger. There we go. Match on a property node that has this polygon property and spatial.algo.within polygon. So that takes a point and the polygon property. So this says find where this point is within the polygon property on a node and return that node. And we should find Montana State University, which we did. Cool, so this allows us to, if we think back to like on the website we eventually want to build, we're gonna see a map, we're gonna click somewhere on the map, and what we wanna do is figure out, okay, well, what parcel does that point belong to? Well, on the back end, this is how we're gonna do it. We're gonna use this spatial algo within polygon, pass in the point that we clicked on the map, figure out what parcel that belongs to, and then annotate the map with that information. Cool. So that's kind of where we left off last time. We were just starting to see how we can use this in our GraphQL API. And to do that, we were using GraphQL Architect. So GraphQL Architect, which we talked about a little bit, this is a fairly new GraphQL Architect. There we go. GitHub.com, GRANDstack, GraphQL Architect. Put that in the chat. So this is a fairly new graph app. So a graph app is a single page application that we can install within Neo4j Desktop. And it allows us to build things like developer tools that make it easier to use certain features of Neo4j. So there's graph apps for lots of different things. I mean, Neo4j browser itself is a graph app. Bloom, if you've seen Neo4j Bloom for graph data visualization. Bloom is a graph app that gives me some really cool graph visualization features. Drop that in the chat. And so GraphQL Architect is just another one of these graph apps that, in this case, allow me to build a GraphQL API using sort of, call it low-code features. Underneath all of this, it's using the same Neo4j GraphQL JS library, so it just makes it easier to run these Node.js GraphQL web servers on top of Neo4j. Cool, so to install GraphQL Architect, what we can do is you can either open this Neo4j desktop link, and that'll deep link into Neo4j browser to help you install it, or we can just copy this link and then in Neo4j desktop, let's just close browser for now. In Neo4j desktop, if we click on this graph applications sidebar item, paste it in here and click install, but I've already installed it. So that's how you install it initially. Then to start it, in the drop down here, choose GraphQL Architect, and it will spin up and connect to the database we have loaded in Neo4j Desktop. Start off, it just gives me these kind of dummy GraphQL type definitions, but then I can quickly infer the schema. This is my saved one from last time, so I'm going to clear that, and then let's infer again. There we go. Okay, so that cleared out what I had saved last time. And so now, let's choose a port. I think I have something running on 4000, so I'll say on port 4007, start GraphQL server. This is going to now start a local GraphQL API for me on localhost 4007. So I can toggle editor, switch over to graphical. So graphical allows me to query this GraphQL API. I can look at the documentation. So I see I have a property entry point. So I can do things like search for properties. Oh, I don't know, just give me sort of the first 10 at random, and let's look at location. Oops, I want curly braces, not square brackets. So latitude, longitude, and then if we have it, let's try the address. Address is null for a lot of our data. That's fine. Let's try city, state, zip if we have it. That's also null for a lot of things too, but that's okay. Okay, so one thing that's cool about the Neo4j GraphQL JS integration is that it adds these filter arguments. So if I look at the query type for the property query field, so that's an entry point into the API. There's a filter argument, which is a property filter. And so I have lots of different filters that are auto-generated for each property. I think we'll clean this up a little bit because we have a lot of values that aren't very useful here. But one thing that we'll notice is we have a location filter as well. So we have location distance that takes a Neo4j point distance filter. So it takes a point and a distance. And this filter allows me to do something very similar to, we jump back to GitHub, something very similar to this query where I can give it a point and a distance and say, only show me properties that are within this distance of this point. So let's give that a try. So I'm going to copy this, this latitude and longitude for what was Montana State University. If I jump back, now I can say filter location look at our documentation here. What I want is location distance. Oops, not. First need a filter. So the filter argument is location distance less than, and then this takes an input that takes a point. I have my latitude and longitude. Oops, looks like too many curly braces there. Latitude and longitude, and then it takes a distance, which is in meters, so 1,000. So this is equivalent to my other query that I was running in Cypher, which is show me all the properties that are within 1 kilometer of Montana State University, but now doing this in GraphQL. Cool, so I'd have to check these to verify, but pretty sure. Okay, and then we can do other filters, you know, for if I'm interested only in houses that have so many square feet, so many bedrooms, and so on. The bedrooms and bathrooms piece we'll talk about later because we didn't have that in the data we were working with previously. So I wrote a scraper that will pull in some of that data. But first, let's finish off working with our GraphQL API. Cool. So if you remember, also last time we added some things to our city type. So if you remember last time, we had something like average value, which was a float, and then we had a cipher directive. Actually, by the way, let me, before I yammer on too far, I want to point out the documentation for Neo4j GraphQL.js. So this is all on GRANDstack.io site, which has the documentation for Neo4j GraphQL.js. And specifically, some of the things we talked about. So there's the filtering arguments that we add. So on the documentation, we have some examples using like a movie schema that has graphical, so you can play around with some of the filtering arguments that are included there. And then also the page on working with spatial data and the point type. There's also some more details in the documentation. And what I'm going to talk about next is adding custom logic to our GraphQL API. So we saw how we can sort of use these CRUD operations, searching for properties, doing things like ordering, pagination, like first offsets, that sort of thing. How we have these auto-generated filters, including distance filters. But what if I have some custom logic that I want to add to my API? And the example we were starting to look at last time is, what if I want to compute the average value for properties in a city? And we can do that using the Cypher GraphQL schema directive, specifically to compute scalar fields. So here's something very similar to what we want to do, where we're adding an average stars field to, this is a schema that has business reviews. So the Cypher statement that we're binding to this field says, find all the reviews for this business and return the average of the stars property on the review node. Cool. So we can do things just by kind of augmenting the generated GraphQL type definitions, which is nice. But one thing that's cool in GraphQL is this idea of type extensions. So type extensions allow us to extend types that are defined elsewhere in the schema. This is really useful if your GraphQL type definitions are split up into multiple files. So here's an example where we have type movie declared, and then later on somewhere in the GraphQL type definitions, we are extending type movie by adding some additional fields. So let's, instead of adding this directly on the type city, let's extend type city, and we'll put average values here. So the reason I like to do this when we're working with Neo4j GraphQL JS, and especially within GraphQL Architect, is it's a common pattern where I'm maybe adding some data to Neo4j, and then I want to go through the infer schema process again, where it'll overwrite my existing type definitions. And so it's nice to be able to have any of my custom logic fields kind of defined up above here. For now, I can just kind of like copy those and then paste them in after I run the type definitions. But I think in future versions of GraphQL Architect, we'll add, I think, probably multiple tabs here so that I can have my type extensions maybe in one pane and then overwrite the inferred schema in another. So this allows me to kind of get like the delta of what's changed in the GraphQL, in the Neo4j database, kind of sync that with my inferred type definitions, and then have my custom logic that I'm adding on somewhere else. So it's nice to be able to keep my GraphQL type definitions then in sync with the database that way. Cool. So anyway, so for average value, it's going to be match this, where this is the city. So I want to know what are all of the property, spell that right, property nodes in the city. And we're going to turn average of p dot total value. Cool. So let's save that and restart our GraphQL API. And now, instead of querying for properties, let's query for cities, all of the names and their average values. And we have an error. What did we do wrong there? Expected and iterable. What did we do wrong there? Expected iterable, but did not find one for city dot average value. Oh yeah, I said that was a list of floats, but it's just a single float, single value for each city. Save that. Restart our API. Let's try that again. There we go. And we can order by average value descending, so show me the most expensive city first. Okay, cool. So that allows us to add computed scalar fields. Another thing we can do is add custom query fields. So every GraphQL schema has a query type. In the case of Nifty GraphQL JS, we generate this query type from your type definitions, and we add a field for each type that you've defined. You can configure that. You can exclude certain types and so on. But we can add custom query fields, which basically just extends the generated query fields that we add. So, for example, let's use this query where we were using the spatial algo within Polygon procedure to find properties where we passed in a point, and that point was then used to find which property, which parcel belonged to that point. So let's call this property, I don't know, for point or something. And this time we're going to pass in field arguments. So latitude, which is going to be a float, and longitude, which is going to be a float. This is going to return a list of property types, and we're going to add the cipher directive. And in this case, we're going to run this cipher query that says, okay, find a property that has Polygon property and spatial algo within Polygon for a point, comparing that point to see where it is within a property that has a Polygon property. But instead of a hard-coded latitude and longitude, we are going to use cipher parameters here, latitude and longitude. Okay, so where are these latitude and longitude cipher parameters coming from? Well, they're just coming from the field arguments here. So the user will specify a latitude and longitude, and then those values will then be passed into this cipher statement. Cool, so let's save this and refresh our GraphQL API, and we'll see if this works. So first off, if we take a look at our query type, we can see we have a new field, property for point, that takes a latitude and longitude. So let's start with that, property for point. Latitude, let's use our same Montana State University example. So latitude 45 something, longitude negative 111 something. Okay, and then this is going to evaluate to a property. So be like city, state, zip, and owner name. And if this works, we should see Montana State University as the property that we've found. And yep, looks like it is. So we can get the location. We kind of already know what the location is, but we can get the boundaries now of the latitude and longitude for the polygon that makes up the boundaries of the parcel. So if we're thinking, okay, from our React web application, we have a map, we click somewhere on the map, it hits our GraphQL API, sends this query that says, find the property for that point. The latitude and longitude that we're going to pass in is going to be wherever I clicked on that map. And what it's going to return then, what our GraphQL API is then going to return to the front end is this. It's going to say, hey, that's Montana State University. Here's all of the latitude and longitude pairs that you need to draw the polygon on the map, so you can see, yep, that's where I clicked. But now here's the parcel that contains the point where you clicked on the map, and tell me more about that property. Cool. So that is good. We are missing some important information though. So from those shape files that we downloaded last time, we got kind of some basic information about each parcel, like the latitude and longitude things, the owner in some cases, the address in some cases, and so on. But what I really want to know is for each property, how many bedrooms does it have? How many bathrooms does it have? How many square feet is the house? How many square feet is the lot? That kind of thing. So that information is available. I'm sure this varies by state and county, but in the case of Montana, the state that we're working with, this information is available in what's called the property record card. So there's a website where I can click through for a given parcel and look at like the history of the appraisals. So for the last 3 years, how much was this house worth? What were the property taxes? For any of the buildings on it, what year was it built? How many bedrooms does it have? How many full baths? How many half baths? And so this is all useful information that we need for our real estate search application. So I wrote a really simple scraper in Python to fetch this information. There's probably some sort of API where you can pull this data down. I couldn't find it, but I found this. So this is easy enough to scrape with beautiful soup. So this is checked in on GitHub. If you want to see how this works, it's in the data directory. It's an IPython notebook for readability. And basically what this does is first it queries Neo4j for each property node and grabs the ID and just returns a big long list of those IDs. Those in the terminology of the property record card site, those are called geocodes. So in this case, we have almost 50,000 geocodes, so 50,000 properties we need to scrape information from. Then there's a couple of functions here. If you look at the URL for this, it takes the geocode in a special kind of format with some dashes in it. So we need to convert from the way that we have that stored in the database to with some dashes. These are the values that I want to scrape off of this site. So things like the category of the property, is it residential, is it commercial, what subdivision is it in, how many square feet is it, how many bedrooms does it have, and that kind of thing. So what we do is we just iterate through this list. The URL is this URL plus the geocode, and then Beautiful Soup. If you're not familiar with Beautiful Soup, it's a great Python library for um, scraping. I'm sure you can use it for other things as well. I've only used it for sort of scraping websites. It gives you lots of different ways to kind of iterate the DOM using either sort of like jQuery style or CSS selectors, or you can kind of walk the DOM with its own sort of Python API. So we do that once for the appraisals, which is this table, this table. So in most cases, I think we have 3 years of appraisals. So this is useful in our application. If you remember, we want to show not only like an estimate of what the house is worth, but we want to show like a chart going back in time a little bit to show how the value of this house has changed over time. So this gives us a little bit of that information going back in time. Oops, where were we? Here. Okay, so we do this twice. We do it once for the appraisals and then once for all the other information like the size of the house, bedrooms, bathrooms, and so on. And then we write to 2 different CSV files. So what I want to do, let's take a look at these CSV files really quick here. Zoom in a little bit. So one is called appraisals. So this one's really simple. It has a bunch of rows, the ID of the property, the year of the appraisal, and then the appraisal consists of a value for the land, for any buildings. This one, I guess, doesn't have any buildings, or maybe it has a worthless building on it, and then the total of the appraisal, and then there's different methods. So they can, I don't know, cost is maybe looking at if they have an actual sales record, or there's various methods for coming up with these appraisals. I don't know what they are. So there's that file, and then there's one called property features. This one has a bit more information. It has the ID of the property, what category it is, the address, subdivision, the date this information was last modified, the neighborhood, lot size, acres. Lot size and acres, it's kind of the same information, right? I think the way this works in the data set is if it is, I don't know, up to like 10,000 square feet or whatever like a normal lot size is, then you'll have square feet listed for lot size. If it's some massive property that's like, I don't know, a ranch or something, then you'll have a value for acres. So this is kind of like an either or. And an acre is what, like 20,000 square feet? Actually, I have no idea how many square feet an acre is. Maybe someone can chime in the chat and let me know. But yeah, an acre is many thousands of square feet. Anyway, the year the house was built, the style, this I think is something like, is it like conventional? Is it a split level? That kind of thing. What sort of heating system it has. This can be important if you live in Montana for the winter to know if you have like electric heat or like gas heat or something. Square foot of the house, and then bathrooms and bedrooms. Okay, cool. So what I want to do is import this data into Neo4j now. So let's go to Neo4j desktop and open up Neo4j browser. Okay, so so by the way, I've already copied these into the right directory. If you remember, manage open terminal. If you remember when we were doing this for with our JSON data, we wanted to have this in the import directory. So I've already copied my appraisals, because I have two. Appraisals full, I guess, is the one I want, and property features full.csv. So I've already copied those where they need to be. If we do pwd, you can see here that open terminal in desktop. The nice thing that does is it opens a terminal specific to this instance of Neo4j that I'm working with. So a nice feature there. You can also get to it from here in the drop down and just select terminal. Okay, anyway, so what we want to do, let's take a look at load.csv with headers from file property features full. And let's just look at the first 10 rows. So the first row is a bunch of nulls, kind of useless. You can see again, this is not perfect. We are missing a lot of data here, but that's fine. If we're missing data, we just won't use it. We just won't set that. So I guess the first thing we might want to think about is there anything in here that we want to pull out into a node rather than just setting properties on the property node itself. So if we go back to GitHub, to Willow, to the README, right? We said property, is in a city. Is there anything else that we might want to pull out of here? And I think in this case, the question I like to ask to say, okay, should this be a property on a node? Should it be a relationship, or should it be a node itself? The question I like to ask is, well, if I can pull this out into a node, and then by traversing through it, is that going to tell me anything useful? If yes, then it should probably be a node. If no, then it probably should just be a property. So let's take acres as an example. If I pull acres out and I say, okay, here's a node that represents 109.02 acres, by traversing through that, am I going to traverse to another property that has exactly 109.02 acres and then is that going to give me something useful? No, it's not. But neighborhood, on the other hand, okay, well, if I have houses grouped by neighborhood, can I traverse from one house to a neighborhood node to then more houses connected to that same neighborhood? Is that going to give me something useful? Well, it might. So for example, one thing we might want to do are find comparable homes. This is useful when we're searching for maybe to try to find a valuation for the property, or if we're trying to just find other houses that a user might be interested in. Well, here's some other houses in the same neighborhood. Yeah, that might be useful. So neighborhood is something we might want to pull out. And then there's no value in this case, but subdivision is also something we might want to pull out. So subdivision and neighborhood, we're going to make those their own nodes. So before we start importing data, I'm going to create a constraint on subdivision, division. I think I spelled that right. Division looks kind of weird, but okay. Create constraint on subdivision. Assert s.name is unique. So this will create a uniqueness constraint for subdivision, and then we'll do the same thing for neighborhood, assert neighborhood dot name is unique. Okay, and now let's start creating some data. So first thing we want to do, and let's go back, let's close these panes and go back to our list here. So each one of these rows has an ID field. That is how we're going to match on our property. So for each row in the CSV file, match on the property, and then we're going to set a bunch of values, a bunch of properties on this property node. I really should have called this parcel or something like that, and instead of saying property a whole bunch of times. Properties become a bit overloaded, but that's okay. If you remember when we were doing load CSV, we just we had this object called value, and we just did something like set p plus equals value. And we didn't have to go through and set each property name individually. And in that case, that was really handy because we didn't have to go through and pull out each field and give it a name. And we can't quite do that here because with load CSV, we don't really have any types. Everything is assumed to be a string. So here, for example, here's acres. Well, acres, this is really a float, but here it is represented as a string in the CSV file. So what we're going to do is go through each of the fields that we want to set as properties on our property node. There's property overloaded again. And we're going to specify the name of the property, and then we're going to cast the value from our row object that comes from the CSV file. We're going to cast that to the type that we want. So for example, we have square feet is going to be 2 integer row dot square feet, and p dot bedrooms what else do we have? Full baths. Same for half baths. I like to line up like that. More readable, I think. Half baths, what else do we have? We have lot size. Lot size is also an integer as a number of square feet of the lot, where square feet is square feet of the house itself. What else? We have acres. Acres is a float, so decimal. You have year built. We have an address. Subdivision we said we're going to pull out. We have a style. We have type of heating. And then we have a category. So this is like if it is residential, if it's commercial, if it's mixed, and so on. Press escape just to get a little bigger view there. Okay, so I think that's good. Maybe give that a little spot check to make sure I didn't spell anything wrong. Yeah, it looks fine. So that's good for the property values that we want to set from the CSV file. But we also need to pull out the neighborhood and subdivision. So for that, we're going to merge on subdivision. So subdivision is going to have a single property, I guess, that's going to be name row.sub. You saw it trying to autocomplete there, capital subdivision, and then it was missing. And if we remember the data we got from our shape files that we converted to GeoJSON and imported, it had subdivision as well. But I think it was missing in some cases. So we'll use this one. So first, merge on subdivision. So if a subdivision node exists with this name for subdivision, we're going to just match. If it doesn't exist, then we're going to merge. And live data concepts says I misspelled to integer. Thank you. Is that this one? To integer. The other ones look good. Cool. Thanks for catching that. Let me know if you see any other typos there. Cool. So subdivision, and then merge to create a relationship where, let's just say in subdivision. Cool, and then we'll do the same for neighborhood. So merge a neighborhood name, and then merge on a relationship to say in neighborhood. And I think I have some arrows backwards here. We want to say where the property is in the subdivision and the property is in neighborhood. So going that way. Okay, cool. So I think that looks okay. So a question for folks, if I run this, are we going to get an error, or is this going to work? I think we're going to get an error, but can anyone tell me what the error is going to be? So let's go ahead and find out. Cannot merge using null property value for name. So what's going on here? So if we remember, we have a bunch of nulls in our data. So like here we don't have subdivision. And the problem is here, we're merging on subdivision where this value, row.subdivision, is null. And that's not something that we can do in Neo4j. Neo4j doesn't know how to handle merging on a null. Null is not a valid value for a property. So we can't set a property value equal to null. I mean, we can do that, but really what happens is it just means that that property is not created. So the semantics of merging on null don't really make sense in this case. So there's a few different ways to handle this case. We could like filter out any rows where subdivision is null. We'd have to do the same for neighborhood. What I like to do in this case is just kind of put in a default value, which we can do with the function coalesce. So coalesce is a function that will evaluate to the first non-null argument that it has passed. So in this case, we can create like an NA, not applicable default value. This will then have the side effect of creating a subdivision node for NA, not applicable, and connect our nodes to it. That's fine. We just have to be kind of aware of that. Anyway, different trade-offs for how we want to handle that. So we'll do the same for neighborhood, and let's see what happens. Okay, so hopefully this will create some data for us. How are we doing on time here? Okay, so let's. I think a goal for the rest of today's session is to finish up our data import with this data that we scraped, and maybe see how we can refresh our GraphQL API, and then next time we will look at connecting our React front end to our GraphQL API and starting to update that. If you remember, so while this is loading, if you remember last time, I guess this was the first session, we started with the GRANDstack starter project, in our case, just connecting it up to a Neo4j sandbox instance. And so our front end was this kind of dashboard application that used some business reviews information. So what we'll start with next time is converting this to instead be a dashboard of business reviews, to instead each one of these components will pull down some information from our GraphQL API using Apollo client and React hooks. And then I think the next step to go from there is to add a map component to start to do some map-based visual analysis of some of this data. Okay, so this is still loading here. I'll give it some time. I just want to make sure that I created the correct constraints and that we're using them so that this isn't going to take forever to run. Neighborhood. So I see a problem. So it looks like for some reason, business category neighborhood, for some reason, we lost our constraint on property. So I'm going to stop this. And looks like we need to recreate our constraint for property, asserting p.id is unique. Create constraint on property, assert p.id is unique. So the reason I did that is now we have an index on property ID. And if you can see here, we're using this match to match on property by ID. And that should be a lot faster if we can take advantage of that index. One thing we can do, if we add an explain to the beginning of our query, we get a visual representation of the query plan. And so what I want to do is make sure that, let's see, can we zoom in a bit? Sort of. what we want to do is make sure that we're using indexes when we're doing more large scale data import. So if I add an explain to the beginning of my Cypher query, I can make sure that I'm not doing a scan operation and make sure that I'm taking advantage of any indexes that I have. So here we're using node unique index seek. That's good. Here we're using another. So this is for property. Then for our merge statements, node unique index seek for subdivision. That's good. And here's node unique index seek for neighborhood. So that way we can make sure that we're using the indexes for creating or merging or matching when we're doing load CSV or any data import. And that's going to help us with performance. And then also, since we have those constraints, make sure that we're not creating duplicate data. Okay, so that was a lot faster this time. That took 27 seconds. So now if let's look at a neighborhood. Just pick one. Well, neighborhoods don't really seem to have a meaningful name. Let's look at subdivisions. That sounds a bit more fun. Okay, so subdivision, here's Lazy Acres subdivision. That sounds nice. So we can traverse out and see, okay, here's some properties connected to Lazy Acres subdivision. If we pick one of these, we can see that it is in the city of West Yellowstone, that it may be in this subdivision, but it's also in this neighborhood. If we traverse out from some of these other nodes, we may find that some of these, in this case, it looks like there's a one-to-one mapping here of neighborhood to subdivision. But it may be in some cases that we have actually some hierarchy here where a property may be in a subdivision and that subdivision is in a neighborhood and that neighborhood is in a city. So instead of kind of the flatter structure we have now, so if we do call DB schema visualization, again, ignore review category and business, do style reset. All right, so here we have kind of like a, I don't know if you want to call this like a star sort of structure where a property is in a city, property is in a subdivision, and a property is in a neighborhood. Really, what we actually have is probably this property is in a subdivision, that subdivision is in a neighborhood, that neighborhood is in a city. So really what we want to represent is some sort of hierarchical structure. We will see how we can fix that later on using the graph data science library and specifically some similarity metrics. But for now, we'll leave it. Okay, so we imported some data. The next thing that we want to do is import some more data from what we scraped. So if we go back to our property record card, we added things like, the living accommodations, how big the house is, that kind of thing. The other piece we want to add are the appraisals. So if we think about how we want to represent this, maybe let's jump into arrows. And let's go in our README. So arrows, if you remember last time we used it, to create this diagram for our graph data model. One thing that's nice about arrows is we can grab the markup for it, check that into version control, and then if I go to export markup, paste that in, I can load my graph. Cool, so what I have now is something like this. Neighborhood, our name is a string, and this is in neighborhood. And this is subdivision. And the relationship is in subdivision. Okay, so I have something like this now, ignoring the listing part and the user part. We haven't quite added those yet. But now I have this data about appraisals. And so for a bunch of different years, I have some values for the appraisal that I want to attach to my property, including a year. So how do we want to model this? Well, I think what we want to do is create an appraisal node that's going to be connected to our property, and it's going to have value properties, what year, land, so that's the appraisal for the land value, building, that's the appraisal for any of the buildings, and then a total, which is the total value of the appraisal, and then a method. And we'll say that the property has appraisal. And then each property, will just have multiple appraisals. So for each year, we're going to have one of these appraisal nodes connected to the property. Appraisal. All right, so something like this. So a property will have an appraisal for 2018, for 2019, 2020, and so on. Cool. There's one other property that we're going to need to add here, and we'll see why in a second. So we're actually going to need to include the property ID, which is a string, on the appraisals. Can anyone tell me why we're going to need to include the property ID on the appraisal node? Well, if we think about this, when we go to import our data, let's take a look at that first of all. So load CSV with headers from file appraisals full, I think it was, .csv as row, return row, limit 10. So I could go through here and just create an appraisal for each one of these rows in the spreadsheet, or in the CSV file rather. And that would then be making the assumption that there aren't any duplicates. Now, I don't really trust the simple Python scraper I wrote or the property record card site well enough to not have generated any duplicates. And also in general, it's a good idea to have idempotent data import. Idempotent, that means that I can run it over and over again, and I don't have any any side effects. If I have the same data and I run my data import, then I have the same data set. It doesn't impact my database. So to do that, I can't just create a node for each one of these rows. I need to use a merge. So I want to like merge on the appraisal. And with merge, we always want to merge on the property or properties that identify uniqueness. And in this case, what identifies uniqueness is a combination of the year and this value, the ID, which is the ID of the property. So what I want to do is something like this. Right, and then like set building, value equal to, right, so on. I want to do something like that. So now you can see why property ID I included here in the data model, even though we have it here on the property, even though I don't have it in here. So property has an ID, it's a string. So that's why we include it as a property on the node here, even though we can find that same value by traversing this has appraisal relationship. Now, as we saw earlier, it's really important to have a constraint in place before we go through our CSV file and start using merge for two reasons. One is for performance. It's going to be faster to do an index lookup to see if that appraisal node already exists. And then also the uniqueness guarantee is going to guarantee data integrity level at the database, not to create any duplicates. So how do we create a constraint when it spans multiple properties? Well, it turns out there's a type of constraint in Neo4j called the node key. Paste this in the docs, or sorry, in the chat. So a node key constraint uses a composite index and asserts that a pair of properties, zoom in here, that a pair of properties both exists on a node and that pair is unique. So that's what we want to do, is create this node key constraint. So create constraint on, in this case, appraisal, R-A-I-S-A-L, assert, and just for clarity here, A is our appraisal. We're going to assert A dot, we're going to call it property ID and A dot year. So asserting that the combination of year and property ID is unique, because for each property, for each year, we're going to have a unique appraisal. So create constraint on a appraisal, assert A.property ID, A.year is a node key. Cool, and now, oops, that's the wrong thing to paste. Going back to load CSV with headers from file, appraisals full.csv as row, turn row limit 10, that's what we had, yep. Cool, so now we can match on our property, looking at the row, and then merge on our appraisal using both property ID, which is row.id, and the year, which is going to be to integer row.year. Cool, so that'll give us unique appraisals. Then we can set a value to integer for row.land. There's total value, row.total, which is this one. Building. Row.building. Line these up. And then the last one is method. To integer row.method. Okay, so that gets us the node. Then we need the relationship. So merge where the property has appraisal A. Cool, so let's give this a once over. Load CSV with headers, appraisal's full is row, match, or the property ID is the ID from our CSV. Now merge on the combination of property ID and year, our appraisal. Set land, total, building, method, merge, property has appraisal. That looks good. Let's give it a run. And let's, while this is running again, if we add explain to our query and take a look at the execution plan, just make sure that, yep, we're using an index, which means we're going to be using our, in this case, node key constraint. We can see it here on appraisal, property ID and year combination. Cool, so this, we should have like 3 years of appraisals for about 50,000 property nodes that we have. So hopefully we should end up creating about 150,000 appraisal nodes here. And yep, that's what we end up with. Took 19 seconds. Cool, so now if we do DB schema visualization, again, ignoring review business category, we have now appraisals. So a property has an appraisal, it's in a neighborhood, it's in a subdivision, it's in a city. Cool, let's take a look again at one of our subdivisions. Here's Lakeview condos. Oh, there's only a single property in that. We can see 3 years of appraisals. Let's do a style reset so we can see some captions there. So the Lakeview condo, it has 3 appraisals. For 2018, the total appraisal was 668,000. The previous year, 640, 640. Cool. So that that looks like what we want, and we can see this Lakeview condo is in this neighborhood. Here's some other houses that are in that same neighborhood, and now we can start to see, oh, here's a different subdivision. So here's another timeshare condo that is in this neighborhood, but these properties are in different subdivisions. So both of these subdivisions are in this neighborhood. So you can see where that hierarchy starts to emerge. So we'll need to start thinking about how we can extract out that hierarchy. But again, that is an exercise for a future time. Cool, so the last thing I want to do now is jump back to GraphQL Architect. So let's switch here to GraphQL Architect, toggle to editor. So what I'm going to do is copy these pieces that I added with custom logic. Going to clear my type definitions. Let's run infer schema again. So now that I've changed data in the database, I want to update the type definition. So now it includes subdivision, neighborhood, appraisal. We can see it also includes things like square foot, number of baths and bedrooms, and so on. We'll add in my type extensions with my custom logic. And let's restart our GraphQL API. Okay, so now what I can do is something like, let's search for properties. Let's look at 10, but I'm going to filter, first 10, pass in a filter, and I'm going to want, I don't know, at least 4 bedrooms. Let's get a massive house. So at least 4 bedrooms, full baths, greater than, oh, I don't know, I'm going to need at least 3 full bathrooms, and we're going to get address in city. We're going to see what city it's in. We're going to see what subdivision it's in. So in subdivision, name. Right. So this is the type of query I might run in my search application, where I'm specifying some of the filters that I want to add. Remember, I can also add in things like within a certain section of the map, within a certain distance, and so on. Right? Maybe I want this to be location distance less than point, latitude and longitude. Oh, and oops, that's my point. So this is Montana State University. So I want a massive minimum 4-bedroom, 3-bath house that is 1 kilometer or less from Montana State University. And I can also look at the recent appraisals, year, total, and we can order our appraisals by year descending, so it gives me the most recent appraisal first. Cool. Oh, and let's be sure we return number of bedrooms and number of full bathrooms and square foot and lot size, and maybe it has some acreage. Okay, so here's a 1,600 square foot house that is 6 bedrooms, 4 baths. It is worth $440,000. Here's the address. It's within 1 kilometer from the university where I want to live. Great. So this is a relevant search result for me. Okay, cool. So I think that is pretty good coverage for today. So just to kind of refresh on what we did today, we took a look at using the spatial algo within Polygon procedure to find properties that belong to a certain point. So point in Polygon, geospatial queries here. We added that to our GraphQL API. We took a look at scraping data using Beautiful Soup in Python from the property record card website. We saw how to import that data into Neo4j, adding things like neighborhood, subdivision, appraisals. We saw how to use GraphQL Architect to keep our GraphQL API in sync with the database and also add in some of our custom logic in the GraphQL API. And then we saw how to structure some GraphQL queries to search for properties using both the filters for things like minimum number of bedrooms and bathrooms, but also how to use the geospatial, in this case, the point distance filter, but also how to use our property for point query field in our GraphQL API. Cool, so that was a lot to cover. I think that was some good progress for today. So I think we'll call it a day here. Next time we will switch to the front end piece of our application. Again, we will start with the skeleton that we have from GRANDstack Starter, and we'll switch this to use our property GraphQL API that we've been working on using Apollo client. And then we'll see about adding a map component so we can search on a map and annotate the map with some of these properties. Cool, so hopefully that was useful. I'll update the GitHub repo, paste the link in one more time. So I'll update the GitHub repo with everything we covered today so you can see that. And then we will see you again next Thursday at 2 p.m. Pacific. So thanks for joining today, and we'll see you next time. Cheers.